So hello everybody. In this presentation I'm going to give you a side report about the latest status of the CSCS infrastructure. So for those of you who don't know us, CSCS is the Swiss National Supercomputing Center. It is located in the south of Switzerland, in Lugano, in the Italian-speaking part. And it was founded in 1991. And we are a department of ETH Zurich, the Polytechnic of Zurich. We have around 140 employees. Most of us are located in Lugano, but we have also an office in Zurich right now. We have around 2,000 users, mainly from academia, and we also have some collaborations with other Swiss institutions, for example, Meta Swiss, PSI, and also other centers like EPFL and ECNWF in Bologna. So the one that you see in the photo is our main office building. In the back of it, there is also the data center where we installed our new Alps infrastructure, which is replacing the old supercomputer called PITSDAINT. So what is the Alps technology? Our idea started with the concept of science as a service. So we designed our infrastructure in a way so that there are many network endpoints which are available to users, and they get access to various resources. And basically, we have a big Cray EX supercomputer onto which we configured several V clusters. V cluster stands for versatile cluster, and they are basically Slurm clusters, but they can also be Kubernetes clusters or other type of environments. Basically, we are trying to have a converge of cloud and HPC. Our hardware is a mix of different architectures, mainly NVIDIA Grace Hopper GPUs, but also we have AMD GPUs, x86 processors, ARM processors, etc. The way that the Cray EX system is managed is with a microservice architecture based on CSM. The network on these systems is a slingshot network, and on top of this, our environment is distributed in several locations, and we are trying to aim for a multi-tenancy infrastructure. So here you can see the photo of the Alps main supercomputer that we run. We actually have more than one Cray EX systems, but this is the biggest one right now. It is a multi-phased installation. We started in 2020. At the moment, the system is complete. We have 10,000 GPUs. Basically, we have around 2,000 nodes. Each of them have 4 GPUs and 4 slingshot network cards. Each of them goes around 200 gigabit per second. So there is a lot of throughput from each compute node. We also have a set of AMD GPUs, and like we recently installed the MI300 ones. So we have 2 different availability zones, one which is HA for the Meteo Swiss workloads, and one which is more simple for a research infrastructure which doesn't need very high availability requirements. The system is liquid cooled all the way to the processors, and as a center we use the water from the lake to cool down our infrastructure. The total envelope of this environment is around 10 megawatt. The peak performance of Alps, which was measured in May 2024, is around 350 petaflop, and we reached the position number 6 in the top 500. We are now running new benchmarks, so we might get different results in the November list. So as this is the last conference, I will try to focus on the storage infrastructure that we are running. So at the moment, we have a mix of technologies. We are focusing mainly on Lastre file systems, which we back up and we do archival using HP DMF onto tape library. The new one which we recently installed is a Spectra Affinity library, but we still have an older IBM TS 4500 library in-house. From Spectra, we also got Black Pearl, which is offering an S3 front end for our tape library. Together with these technologies, we are also installing a VAST system, which we are going to use in the future for our users' folders. At the moment, we have them on Lastre, though. We also have Ceph. We integrated it with the cache for running the grid workloads. And we also have other technologies such as Globus Online, and we still have some older storages based on IBM products such as Spectrum Scale and Spectrum Protect, but we are on the way to decommission them eventually. So this is a high-level picture of how the ALPS concept works. Basically, you can see in green, there is a set of Cray EX systems. And basically, we have, I think, 4 or 5 different Cray EX systems. The biggest one is the ALPS infrastructure that I showed you before, but also we have some smaller ones for Meteo and test and other type of users. Then you can see in green, there is a set of tenants. So these are basically our customers and how we should divide them. So we have a big tenant, which is for the university user base, but then we have some smaller tenants which are for some specific customers such as Meteor Swiss and PSI, and also CTA and SKA, if you heard of them. And each tenant is assigned a set of V clusters. So as I said before, each V cluster is either a Slurm cluster or a Kubernetes environment. And so how do we attach storage to this type of diverse environment? So basically we have, initially we bought a very big storage called Capstore that I will tell you soon about. And then we added smaller storages which have been attached more in a ad hoc fashion where it is needed. So the idea is that we try to keep the environment as flexible as possible. So here is a more detailed picture of how our infrastructure looks like at the moment. So if you see here, the big green balloon is ALPS, and there is several Lastre file systems, the ones in gray, which are attached directly to the Slingshot network. The biggest one is called Capstore. It stands for Capacity Storage, and but then there is also smaller ones like the MCH store systems. So there is 3 of them, and these are used by the Swiss Meteorological Service. And as you can see, they are attached also to other 2 Cray EX systems. There is ALPS-M and ALPS-C. The interesting thing here is that ALPS-C is actually located in a different city in Switzerland, around 300 kilometers from Lugano. And we are doing some cross mounts across sites, so I will tell you more about it later. Then we have, in light gray here on the left, there is IOP Store, which is the system that we dedicate mainly for AI use. It's a SSD-based cluster store system. Then we have PSI Store, which is a hybrid between hard drives and SSDs, which we dedicated to the customer PSI. In this case, basically we have the PSI network, which extends inside of ALPS over long distance, and basically they have their IPs in our environment, and they have a dedicated set of nodes which we segregated using a VLAN. Then on the bottom left, on the bottom right, you have pre-Alps and Alt. These are the like smaller test systems that we have. And we also have a Cray EX, which we installed recently in Bologna at ECMWF. And the idea is that we are going to do some pre-processing of weather data there, and then send some of it to Alps, where we will do some work with GPUs on it. Then here on the bottom left, we have the DMF installation, which is using some LNet nodes to connect to the various environments, and it is backing up data to the Tfinity library. So here is a list of our hardware. So here you can see on the left only half of Capstor. So this is a very big storage system based on hard drives. It's got 11 racks of servers and disks, and the total hardware capacity raw is around 130 petabyte. The usable one is over 90 petabyte, and because we are using read-rate. There is a total of over 8,000 hard drives. They're all 16 terabyte hard drives, spread over 80 disk enclosures. We have a total of 6 MDS servers and 80 OSS. This file system is at the moment serving both Scratch users and long-term storage, and we divide them. We divided these folders onto different MDSs for preserving the throughput of each of them. And the performance that we measure with IOR is over 1 terabyte per second. In read, we actually almost reach 1.2 terabyte. And the IOPS are in line with what the hard drives provide, so it's around 1.5 million IOPS. And from here, I'm going to connect to the right side of the picture where you can see IOPS Store, which is instead a system fully made of SSD drives. So in here, the main difference compared to Capstor is the speed of IOPS. So you can see that we can reach 24 million IOPS write and around 9 million IOPS read. But this system is actually not even a full rack. It's like half a rack, and also the I/O bandwidth is not so different from the one of Capstor. So we can reach 400 gigabyte per second write and almost 800 gigabyte per second read. So there is a raw capacity of 7.2 petabyte and around 240 NVMe devices. Each of them is 30 terabyte. So, and then here we have a few smaller systems. We have 3 systems for Meteo Swiss, as I said. So the main idea of having dedicated Meteo Swiss systems is that if we take down the big storage, Capstor, then they can keep running. So it's mainly a availability decision. And these systems are around 1.2 peta raw. The performance is of course slower, but this is enough for what they need. So it has around 21 gigabyte per second write and read. Then on the right side, you see the PSI store, which is the storage that we built for the customer here on top left. So it's a hybrid between SSDs and HDDs. It is dedicated to them, and it sits on their own VLAN. On this system, we configured OST pools, and there is around 300 tera SSDs and 13 peta hard drives. Just one note, all the SSD systems we have, we decided to configure them in RAID 10 to maximize the IOPS performance. Then we have a few other systems. So we have CubeStore, which is the one that we have installed in Bologna at ECNWF. It's around 2 peta raw. And then we have Brett. It's a small L300 system which we're using as a test environment at the moment. And then we have another small flash systems which was provided by DDN. And we still have like 5 Sonexion and DDN systems, which we are currently decommissioning. So this is mainly the storage of the old supercomputer PISDAINT and of the old Meteor system. So they will likely be decommissioned within a month or two from now. So I mentioned that we do backups and archival with the HP DMF. So this is you can see the system here in the photo in the middle. It's a full rack of hardware, and we use it for backups of the users and store file systems. The policy there is that we run the backups every 24 hours, and we create 3 copies on tape, and then in the files which have been deleted, they stay for a maximum of 100 days. We also have a use for it as a HSM for archiving data. So basically, every file which gets written into the archive folder, as long as it is in a zipped format and bigger than 1 giga, then it gets offloaded to tape once a day. Then we are also writing our own scripts to do cleanup policies on the Scratch file systems, and we are pretty much querying the DMF database, and which has a live state, pretty much like a live mirror of our metadata service status. And from there we go and find which files have not been touched for more than 30 days. And then we go and clean them up. In terms of hardware, our DMF installation is made out of 1 management node, 5 database nodes, which use Cassandra. It's a replicated database from Apache. And on top of this, there is also some, basically like a queuing system based on Marathon and Mesos. And then we have 2 data mover servers which are attached to the tape library, and 2 data mover servers which are attached to the zerowatt storage, which is this set of JBots at the bottom of the picture. This is pretty much a set of hard drives which are seen as normal tapes. So they have the same life cycle as tapes. On the right, you can see our Tfinity tape library, which has at the moment around 40 petabytes of storage, and 20 drives assigned to DMF. The zerowatt storage is around 3.4 peta. So here is a picture showing how the structure of folders is made on our main storage capstore. So we divide it in user, Scratch, and store and archive, and then we have a sub-layer of folders which represent our tenants, and then in some cases we also have other customers, and then you have users and projects. We create these folders using custom scripts. We divide them onto several metadata servers. We use the DNE one. We also enable ACLs for giving access to the user support to different user data. We enable project quotas, and when basically we notice some complaints from users about the metadata performance, so we suggest them to compile on TempFS, and we use SquashFS for some specific cases where there is some very high metadata workloads. Basically, people can create files which sit on the OSTs, and then they have their own file system inside of those. So I'm a bit running out of time, so I'll try to be fast. Basically, basically, since we have this multi-tenancy environment, we have two use cases. One is to have clusters on which we have root and we give access to users in a traditional way, and this is working quite fine. Then there is other need where customers want to have root on our vClusters. We explored the different technologies here, like different features of Lustre, but we ended up having different, totally different storage for these kind of customers, because we found some limitations in the way that you can configure Lustre that didn't fit our setup. About network configuration, we have dual mode TCP and KFI. We can set up priorities using the UDSP commands. Here is a picture of how we do the long distance mounts. So we run some benchmarks from Lausanne to Lugano. It's around 300 kilometers. And basically we have something like a VPN over long distance, which is going over the internet. And we managed to saturate the links with IOR, with big files. So we can write like 16 gigabytes per second. And but of course, if you do this with smaller files, then you have much lower performance because the latency is higher. We didn't do any special tunings on Lustre level. I'm going to be quick. So we have, for the monitoring part, we use Nagios and Grafana, and these are the stats that we measure. And something interesting, we have been configuring Lustre job stats to go and find how the users use our system, who are the one who are saturating it. And we have some scripts which collect data from the OSTs, and we collect these kind of views, and then we go and filter them based on the vCluster of origin and the type of user and node. We also do reporting with Kibana using project quotas. And for data movement, we do internal transfer using dedicated Slurm queues. There is 4 servers for this. And for external data transfer, we use Globus Online. Future work, so something that we would like to implement soon is notification for when users pass the soft quotas. At the moment, Lustre doesn't really give you any kind of notification when you pass the soft quota. You need to look it yourself. So we want to write some kind of possibly automated email system or something in the command line. We are interested in trying Lustre NRS TBF for doing QoS and limiting the annoying users. And so, yeah, because of the metadata limitations we see on Lustre, we are thinking of moving the user's home directory to VAST, because it also offers snapshots out of the box. And we are increasing work with Black Pearl S3. We want to try NVMe over Fabric. And we are also investigating Firecrest, which is our tool, like an API over Slurm, to do data movement. Okay. Thank you for your attention. Do you have any questions? I was running a bit in the end because I was running out of time. So.
Yes, I'm interested in how you are handling multiple users which have different projects and groups. How are you handling the quotas for these users?
Okay, so we use the Lustre project quotas. We have basically a database which is keeping track of the project IDs and which folder they are assigned to. And we are also integrating all this part with our accounting system. So we have an old tool which we have been developing for years at CSCS, but we are also trying to transition to an international effort called the Valdur. It's a tool that is being developed and can be used for doing accounting onto your systems. Yeah.
Okay. Sorry. So you said that you are Switzerland whether center need to have the data operational and work even if Capstore is not online. So are you cloning data from MH Store to Capstore?
Yes, so basically, these Meteor Swiss customer, they have their own scripts which are doing rsync of data between different file systems regularly. So, for the Meteor service, they run their simulations once every, I don't remember, 6 hours or 3 hours, and then at the end of the simulation, they move the data around so that it's always in sync.
Okay, thanks.
Yeah.
This migration towards VAST, was that mostly because of the snapshot function?
Yeah, so because we are actually coming from GPFS, where we had the snapshots and users really liked them, and then we decided to move to Lastre, and it turns out that we don't have them enabled. We don't do Lastre over ZFS and so on. So we prefer to go to VAST. And then also people are complaining about performance in our environment for the metadata I/O, and we think that it might scale better. But
right. Yes, thank you.
So, not to get into a discussion about that, is that because the Lustre file systems are disk-based and the VAST is flash-based?
of course.
Right. But anyways, my original question was about the quota notification, right? At one time, we were developing that to do notification, but we figured that the notifications would only go to the batch job that's running and the users wouldn't see it anyways. So do you think that that's actually useful, or would it be better just to have in the login script, it prints out the user's quota usage at the user space rather than from the file system?
Probably we're going to do it in the login time. I think this is probably the easiest way to go. Also better than sending out emails or these kind of things, because it's always dangerous to do this automated email sending.
Yeah, I was thinking like in the ext4 quota, it will print a message directly onto the console screen, and we did actually implement that, but then we figured it's actually not very useful because it will go to the compute node.
Yeah.
Right.
So I have one question about the scripts you are using to clean up the Scratch file system, which is based on DMF.
Yeah, we are working on them. They're not in production yet, but
Okay.
Yeah.
So my question was if how much time does it take to scan the file system?
Okay, so
I don't know if you know that because it's not in production.
Yeah, so from what basically our DMF is doing scans once a month, but then for the rest of the time we read the changelogs directly from Lustre. So we have changelogs enabled on the whole file system at the moment, and then when we do the queries to find the old files, we query the database of DMF.
Okay.
And then this takes some time.
Yeah, that's my point.
Yeah.
So you know the time of the.
I think when I was doing some tests, our file system is not full yet, but it takes maybe half an hour or something.
Okay.